Alright, today let us formally solve this problem of a continuous time random walk on a lattice in d dimensions. Just to be specific, let us take a hypercubic lattice. So here is the problem we are going to solve. It is a continuous time random walk on a hypercubic lattice in d dimensions. And we could specialize to d equal to 1, 2, 3, etc., etc. Okay. So just to recapitulate, we already know a lot about this. What I would like to do is to write the formal solution down. It is fairly straightforward to do it for a class of continuous time random walks governed by some renewal process in time, and then we will look at the diffusive behavior, the first moments and second moments of the displacement and so on, and understand how diffusion comes about in this case. So all the while we will have the Markov case as a check on our calculations, because we must reduce to the known results in the Markovian random walk case, which we have solved completely. Okay. So here is what happens. Let me denote by J an element of hypercubic lattice in d dimensions labeled by the integers, infinite lattice. So this J is shorthand for J1, J2 up to Jd, where these are all integers. Okay. So that is a lattice point, and we are going to look at walks which by translation invariance we start at the origin in this d dimensional lattice and we take steps in time. Now the first thing is we ask what is the probability of being at the site j at time n. So just to avoid confusion with what happens in continuous time, let me put the subscript outside to show that this is equal to the probability of being probability of being at of the walker being at j at time n, given that the walker was at the origin at time 0. Okay. We already know this. We know this is some combinatorial factor. It depends on whether there is a bias in the problem or not. We already know what this quantity is. It is some multinomial coefficient, because remember that in the case of one dimension it was just a binomial coefficient with some factors which depended on the bias to the right or to the left, etc. We could as well take a bias in this problem also. So let us suppose that you have bias factors alpha I and beta I equal to 1 minus alpha I. So these are bias factors where I is any one of these directions. Okay. So in the dimensionality 1 to d, any one of them could have a bias, but we also need to know the total probability must be 1. So we also need to write summation I equal to 1 to d alpha I plus beta I, sorry, alpha I and beta I. In general, after you sum, this is equal to 1. So in each Cartesian component you have a bias and the total probability of a jump out of a site into any one of its nearest neighbor sites is equal to 1. Okay. So each of these is a fraction. The unbiased case, the unbiased case would be every one of these factors is equal to 1 over 2d alpha I equal to beta I. Okay. So it says if you are in 3 dimensions, for example, there are 6 nearest neighbors and the probability of jumping right or left, each of these is 1/6 or top or bottom, etc. Okay. So this is some multinomial coefficient. In fact, we know what this fellow is explicitly. We looked at its generating function, and let me call the generating function, let us call that g sub n of z1 up to zd. This is equal to a summation over all components of j, elements of zd, over all the integers for each component Pn of j Z1 to the J1 dot 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 ZD to the JD. That is the generating function. What is the random variable here? J is the random variable. You are given a time and this components, the components of J, they are random numbers, they are random integers. You want to know which site you ended up at, etc. And this is the generating function. Okay. This coefficient here, as we know, is a multinomial coefficient, right. We already know what this Pj looks like. We know what this generating function looks like. Remember, for one dimension this was P times Z, alpha times Z plus beta times Z inverse to the power n. So in the general case, this quantity here is equal to summation I equal to 1 to D alpha I Zi plus beta I over Zi, the whole thing to the power n, because this is the generating function for a single step, which could be in any one of the 2D directions. Okay. So we already know this, and therefore what you are asking for is, of this quantity, when you take this fellow and you expand it in powers of each of the z's, the coefficient of this combination is this quantity which you want here. So it is a multinomial coefficient. Okay. So let us give this fellow a name. This is equal to g of, let us collectively call it z to the power n. Okay. I want to make the notation straight, that is the reason I am taking pains to do this, so that this is just a shorthand for Z1, Z2 up to Zd. Okay. Now let us introduce, so this in a sense this problem is trivial. We know how to solve it. Once you know how to make a multinomial expansion, this identifying this quantity is trivial. Okay. Now let us ask what happens if we put continuous time on this, right. So let us go to continuous time. Okay. And the way to do this is very simple. Now I ask, what is the probability of being at the site j at time t? Since t is a continuous variable, I put this index inside here. Okay. This is obviously equal to a summation over n from 0 to infinity in principle Pn j times w of n comma t, where this fellow here is the probability of n jumps in the time interval 0t. Exactly n jumps, and you are going to allow for all possibilities, so you sum over n. Okay. Remember that different jump events are independent events. So the probability that you have 10 jumps in time t is distinct from the probability that you have 15 jumps and so on. And these are mutually exclusive events, the number of jumps, and therefore I sum over all these guys. Okay. So I have separated out the spatial and the temporal parts. All the time dependence is sitting here. The space part is right here, and that is just pure combinatorial factors. Now you can generalize this to other lattices. You do not need this hypercubic lattice. You have to tell me what is the quote unquote generating function or characteristic function for a single event, jump event, and that is what this quantity is. So on any lattice you can find out what are the nearest neighbor vectors, etc., and find out what this quantity is. Okay. And after that you are guaranteed that since the jumps are independent of each other, this is the generating function for this probability distribution. So now you could ask, what happens if the system remembers its previous jump and so on? All that is happening in time. So that is going here, that input is going here. So the jumps could all be uncorrelated, correlated with each other, and that will show up in w of n comma t. Okay. So as it stands, This is the very general framework out here. Now we can ask what about, what can we say about the generating function for this. So let me call, I need a new symbol, so let us call it L of z comma t to be equal to the generating function for this. This is equal to summation over j all lattice points j over zd p of jt times z1 to the j1 zd to the jd. That is this fellow here. It is the continuous time analog of this generating function here. Okay. So instead of p of pn of j, I got p of j comma t. Okay. So what I have to do is to multiply this by z1, z2, etc., this factor, and sum over all the j's, components of j's. And when I do that, this becomes equal to summation n equal to 0 to infinity w of n comma t, and then here I have to multiply this by these factors and sum it, but that factor we already know explicitly. It is this guy gn of z. So it is just gn of z here, because I multiply this by these things and sum over all the j's, and that gives me this. But this fellow is already known to me in terms of this characteristic function g of z. So finally I get this is equal to summation n equal to 0 to infinity w of n comma t g of z to the power n. Okay. I still do not know anything about this. I have not specified anything about it at all. Okay. But I have a formal expression of this kind. Right. Now w of n comma t is the probability of the distribution of the random variable n, which is the number of jumps in any given time interval t. Okay. So we can define a generating function for that quantity. So let us define, so w of n comma t generating function h of xi and t, this is equal to summation n equal to 0 to infinity w of n comma t some xi to the power n. I do not want to put a z here, a z here, because I use z for the space variables conjugate. So this is the definition of the generating function of this probability distribution in n. Okay. So once I do that, it is clear what this is. This is by definition now equal to h of g of z comma t. Because it is just this to the power n. Okay. So in principle the problem is solved, because if you give me this characteristic function or generating function little g, which depends on the lattice structure, what are the nearest neighbors, etc., and you give me the statistics of this number of jumps in time t, I compute its generating function, and there it is, and I write that in that expression. That gives me the generating function for p of j comma t, which is what I want to find. So once you have this L, which is this crazy power series in multiple variables, formally we can write what its inversion is. So p of j comma t is equal to the coefficient of z1 to the j1, z2 to the j2, etc., till zd to the power jd, right. And the moment you have an expansion of this kind, it is a Laurent expansion, because there are positive and negative powers of each z. This can be written now as a product from I equal to 1 to d, 1 over 2 pi I, an integral around the origin dzi over zi to the ji plus 1 times this guy here, h of g of z product acting on that. So you're just inverting this Laurent transform, this Laurent series to find the coefficients. This is around a small circle around the origin in the zi plane, and you got to do this for each of the zi's. In principle you got the answer. Or you have to differentiate it a sufficient number of times. So some suitable derivative of this quantity or of this quantity with respect to each of the zi's will give, at zi equal to 0, will give me the coefficients, right. But the difficulty with that is that you got negative powers of z, so therefore that is not a trick which is easily doable. This is a much more reasonable formula. So that is it. This solves the problem. But now let us see whether we can do something more in this matter. In particular, I want to say something about w of n comma t, and I want to say that it is a renewal process. W of n t given by a renewal process. That is what a continuous time random walk is. In other words, there is a certain function, a waiting time density, which tells you the density that in time for the random interval between two jumps. So the idea is that if you give me time 0 and t, the first jump may occur here, the second may occur here, tn minus 1 and so on. This interval between jumps, successive jumps, is given by specifying a waiting time density, which is the same for all the intervals. Okay. So we introduce a waiting time or holding time density, let us call it psi of t. Okay. So it says if you start at t equal to 0, then the probability that you have a jump between t and t plus dt is psi of t dt. Okay. And it is obvious that psi of t must decrease as a function of time. Clearly you wait long enough, there is going to be a jump. It is a density, so psi of t must be non-negative. Its integral from 0 to infinity must be 1. It is a normalized probability density function. So these are the properties we require of it. The Markov case is given by an exponential waiting time density, as I mentioned. And it is not hard to see then that w of n comma t will be a Poisson distribution with intensity lambda. Okay. But we will do it more generally than that. Does not have to be exponential, just has to satisfy these conditions at all. What happens then? Because the waiting time density is the same for all of these guys, that is why it is called a renewal process with a common waiting time density. I could generalize this a little bit by saying this jump has a waiting time density different from the second, different from the third, etc. But in the simplest instance, that is not what we look at. We look at just the simplest case where you got a common waiting time density, okay, not necessarily exponential. Okay. Then it is clear that in this geometry here, T1 is less than T2 is less than, etc., etc. It is clear that this T1 appears anywhere between 0 and T2, T2 appears anywhere between T1 and T3 and so on, and it is in the form of a convolution because these intervals, the size are the arguments for the size, right. So it is immediately clear that if you take Laplace transforms and you write w tilde of n comma s, s being the transform variable, it is a convolution. After all, this guy here has a psi of T1, this fellow here has a psi of T2 minus T1, because that is the time you waited for, and so on. Till out here you have a psi of Tn minus Tn minus 1, and it is a convolution of all these fellows because each Ti is bounded by the next Ti plus 1 in the upper limit, right. So there are n of these guys, so it is immediately clear that this is psi tilde of s to the power n, but we got to be a little careful. That is not W tilde of n comma s, because you can ask what happens if n is 0. Then you need the probability that in the time interval t no events have occurred at all, nothing has happened at all. And what would that probability be? Because if I just took this to be the case, W tilde of 0 comma s is 1, and the inverse Laplace transform of 1 is a delta function. That is not what is happening at all, right. So what is the correct situation? What is the correct W tilde of W of 0 t? What is this equal to? Nothing should happen in this interval, right. If a jump occurs, it occurs with density psi of t. So this must be equal to 1 minus integral 0 to t dt prime psi of t prime. That is the total probability that a jump occurs in time t, and 1 minus that is the probability that no jump occurs. Okay. What is the Laplace transform of this guy? What is the Laplace transform of 1? 1 over s, yeah, 1 over s minus the transform of this guy is the convolution of 1 times psi of t. So it is 1 over s times psi tilde of s, right. The Laplace transform of this integral is psi tilde of s over s. When you differentiate you multiply by s, when you integrate you divide by s. Okay. So this in fact is the correct answer. So this is 1 minus psi tilde of s over s, and check this against the case we already know, against the Markovian case, Markov case. Psi of t equal to lambda e to the minus lambda t, where lambda is some positive constant, right. This is guaranteed to give you immediately, trivial to check, that W of n comma t is going to be the correct answer, which is a Poisson distribution. And what is W of 0 comma t when you have such a Poisson distribution? W of n comma t is lambda t to the n over n factorial e to the minus lambda t. So what is W of 0 comma t? E to the minus lambda t. You should it should come out, because this will imply that psi tilde of s lambda over s plus lambda 1 minus psi tilde of s over s is this fellow here. It is 1 over s plus lambda. So that tells you that W of 0 t equal to e to the minus lambda. So that checks. That checks. So indeed that is the correct answer for W tilde of 0 comma s. Otherwise you end up with this inconsistency that you have a delta function, it jumps immediately, which is not true. W of 0 comma t has a delta function at t and then it is 0 thereafter. It is not true, right. Okay. So what is the correct expression now for this W tilde of n comma s? We took into account a jump here, a jump here, a jump here, a jump here with this convolution, but we must be careful. We want W of n comma t is the probability density probability that exactly n jumps have occurred in time interval t. So nothing should happen here, nothing should happen here. So if I call this the probability that nothing happens here, call it phi of t, it is a w of 0 comma t actually, you have to multiply by that, that also is in the convolution, right. So the correct expression is this times 1 minus psi tilde of s over s. That is the correct expression for w tilde. Of course, if you put n equal to 0, you end up with this correctly. Okay. So we are all set. We have an expression for w tilde and therefore we know what h is, and let us put that in and see what happens. So we have h of xi t equal to summation n equal to 0 to infinity w of n t xi to the power n, but this is 1 so therefore h tilde of xi s equal to summation n equal to 0 to infinity w tilde, which of course is very conveniently 1 minus psi tilde of s over s times xi times psi tilde of s to the power n, which is a geometric series. So that is trivially summed, and this gives you 1 minus psi tilde of s divided by s times 1 minus xi times psi tilde of s. Okay. And therefore finally we have our L of z comma s Laplace transform. This is the generating function for p of j comma t. Now I take its Laplace transform instead. That is equal to 1 minus psi tilde of s divided by s times 1 minus not xi but g of z psi tilde of s. And that is the Laplace transform with respect to time of the generating function of my probability distribution p of j comma t. Okay. Quote unquote, all I have to do is to invert this transform and to invert the power series itself, I mean the Laurent series itself. But in principle that is a solution, it actually finishes it completely, explicitly. What we need to now do is to ask how do we extract information from this. In principle we can solve this once again, but let us first check the Markovian case quickly and see whether this works or not. So again Markov case, psi tilde of s equal to lambda over s plus lambda. So what does this give you for L? This is equal to 1 minus this guy is s over s plus lambda, and the s cancels out, so it is 1 over s plus lambda 1 over 1 minus g of z psi tilde of s. So there is a lambda sitting there over s plus lambda. So let us take this and write it as s plus lambda minus this guy, and this s plus lambda goes away, right, and I take out this lambda and I get 1 minus g of z. And of course we can invert this transform in time. 1 over s plus anything, s plus a constant independent of s is e to the minus that constant times t, right. So that immediately tells us, so it says L tilde L of z t equal to e to the minus lambda t e to the lambda g of z lambda t times g of z, and that is it. Of course, if you look at the case we are looking at, this is e to the minus lambda t on this hypercubic lattice, e to the lambda t summation I equal to 1 to d alpha I zi plus beta I zi inverse. Okay. And what is the usual trick? Well, take out alpha I beta I, so write this as alpha I beta I times alpha I over beta I square root zi plus square root beta I over alpha I 1 over zi. And that is the generating function for, pardon me, for which one? Yes. So what is the function that you get? This is a generating function for the modified Bessel function. We know that, of course, right? So recall exactly the Skellam distribution. So recall that e to the power xi over 2 z plus 1 over z equal to summation j equal to minus infinity to infinity I j of xi z to the power j. And that is the modified Bessel function on the with the integer order, and I minus j is identically equal to I plus j. So this is a product. So this is equal to e to the minus lambda t product I equal to 1 to d. Shouldn't forget this factor. So alpha I over beta I to the j I over 2, that is sitting there, and then I j sub I of twice root alpha I beta I lambda. So it is a product of these Bessel functions. That is the solution to the biased random walk in a hypercubic lattice, the Markovian case. So this general answer, this guy here reproduces that immediately. But you do not always have such a simple function to invert unless this is 1 over s plus lambda or something simple. This is not such a trivial matter to invert this always. In general, the solution could be much more complicated. Right? In particular, we are interested in the asymptotic behavior of both the mean displacement and the mean square displacement or the variance. Now we know by symmetry that if you do not have a bias in the problem, if each alpha I equal to beta I equal to 1 over 2d, then there is no bias at all and the mean displacement should go to 0. Let us see if that emerges. Let us see if that emerges from this general case even without inverting the transform. You see, what I want is j, any one of the j's, so ji as a function of t. This is equal to a summation over all the j's p of jt times j sub I, any particular ji. Right? So the transform of this guy ji of s transform in t is with a p tilde here, so over j p tilde of j s j sub I. I need to pull down a ji. How do I do that from the generating function? We already have a generating function because this fellow here, if you recall, this guy equal to summation over j element of this d-dimensional lattice p of j comma s p tilde and then z1 to the j1 zd to the jd. I want to pull this down, pull the 1 power of ji down. What should I do? Differentiate with respect to that particular z and then set all the z's equal to 1. So this is equal to delta L over delta zi at all the z equal to 1. So this is 1 1 1 1, all z components are equal to 1. Now when I differentiate that, what is going to happen? Recall that we had a formula for this fellow here. This was, you have to remind me of what this formula was, 1 minus psi tilde of s in general divided by s times 1 minus, now I am not very sure what really happened. There was a g of z and then psi tilde of s. Right? And we have to differentiate this and then set z equal to 1, all the z components equal to 1. You differentiate this guy, remember that, so if you differentiate this fellow here, delta L over delta Z I, L tilde, is going to have all these factors as before, but it is going to have a g prime of Z on top with respect to that particular Z. Right? And this g, so I will not belabor the point very much, because if you put g, all the z's equal to 1, what do you get here? You get summation alpha I plus beta I, which is equal to 1. So it is very clear that g of 1 equal to 1. Right? So after you differentiate, you are going to put g equal to 1. So you are going to get 1 minus psi tilde divided by this fellow squared. You put z equal to 1, it cancels one factor between top and bottom. But you are going to have this factor here, and remember the corresponding I dependence was in the form alpha Zi plus beta over Zi plus other stuff. But when I differentiate this, I get alpha Zi minus beta over Zi squared, and I put all Zi is equal to 1. So it is immediately clear that this fellow is going to be proportional to alpha I minus beta I. That is going to come out as a factor. Indeed it should, because if there is no bias in that direction, that particular coordinate's average value must be 0. So this is where it is coming from. Okay. Moreover, if it is a Markovian walk, we know it must be linear, and that emerges also, because what is psi tilde of 0 equal to? That is the integral of psi of t from 0 to infinity. So it must be 1, right. So this must be 1. But now I ask, what is psi tilde? So you got to be careful. When you put s equal to 0, this vanishes here. So you have to ask, what is the small s behavior of psi tilde of s? Now it is clear that in the Markov case, if psi tilde of s equal to lambda over s plus lambda, this is equal to, I pull out a lambda, and equal to 1 plus s over lambda inverse, this is equal to 1 minus s over lambda plus order s squared near s equal to 0. So you have to be careful, because we have got factors like 1 minus psi tilde of s, so we better be careful. So now look at what happens if you differentiate. This guy gives me alpha minus beta multiplied by a psi tilde, but that is equal to 1 if I put s equal to 0. This gives me a 1 over 1 minus psi tilde between this and the square of this. So that gives me a factor s. This gives me an s. So the whole thing for small s is going like 1 over s squared. What is the inverse Laplace transform of 1 over s squared? It is a ramp function, it is t, because we know that the t to the power alpha, the transform is 1 over s to the alpha plus 1. So if you have large t behavior like that, you have small s behavior like this. That is a useful thing to remember. So you got a 1 over s squared, so the whole thing, it will tell you that ji of t average for t tending to infinity will go like this. In general, as long as psi tilde of s has an expansion 1 plus order s, as long as that, this factor is not relevant. I mean, the fact that in this case it happens with this is not relevant. So if psi tilde of s is analytic at s equal to 0, the leading term must be 1 at s equal to 0 by conservation of probability. The next term, if it is analytic, must be of order s. There is a Taylor series which exists. Then you immediately get this result. Now look at what happens to diffusive behavior. In the case of diffusive behavior, we must look at the variance, but let us be simple and look at just the mean square displacement. Let us put the bias factor equal to 0. So all alpha is equal to beta i's and so on, and then this g of z just becomes zi plus 1 over zi summed over 1 over 2d outside common factor. So let us look at the unbiased case and see how diffusion comes out. So we want ji squared of t. So ji squared of s has a square here. You still have this, but now you want twice ji, you want to differentiate, right? What should you do? If you differentiate once, you are going to get a ji. If you differentiate a second time, you are going to get a ji times ji minus 1. So a second derivative is really d2 L tilde over d zi2 is going to give you this moment ji times ji minus 1. But that is ji squared average minus ji average, but if there is no bias, ji average is 0. What does that imply? It says g prime, remember this, no bias implies g prime of z equal to 1 equal to 0, because each time you differentiate this fellow you get alpha minus beta over z squared, but if alpha equal to beta, this is 1 minus 1 over z squared, you put z equal to 1, it goes to 0, right. So what I am saying is g of z is 1 over 2d alpha 1 plus z1 plus beta 1 over z1 plus dot dot dot. Okay. If I differentiate this guy, in the unbiased case it is just this. If I differentiate this, g prime of zi equal to 1 over 2d. If I differentiate with respect to one of the z's, it is zi minus 1 over zi squared. This is delta dz over delta zi. So g prime, if I put z equal to 1, vanishes at that stage. Therefore it is sufficient to take the second derivative of this guy, and that will tell me what the behavior of this is at long times immediately. So let us go back and quickly do that. I have L tilde of z s equal to 1 minus psi tilde of s over s times 1 minus g of z psi tilde of s. I have to differentiate this twice. I differentiate it once, I am going to get a g prime on top. This fellow squared, and then I am going to get psi tilde times g prime of z. I use prime for the partial derivative with respect to one of the zi's for the moment. I differentiate second time, I differentiate this guy, and I am going to get another g prime factor on top, but g prime is equal to 0 at z equal to 1, so that does not contribute, and in the second derivative it is only the second derivative of this that contributes. But what is the second derivative of this? It is just 2 over zi cubed, and I put zi equal to 1, so it is just some number 2, some finite number. So this guy goes, the second derivative of this fellow at z equal to 1, 1, this goes to 1 minus psi tilde psi tilde over times a number here times s into 1 minus psi tilde, the square, this goes away, that is it, times a number into some number times that. There is no s dependence. What this is now what? This is equal to ji squared. What does it do for small s? That will tell me what this guy does at the inverse transform does at long t. What does it do at small? What does this fellow do at s equal to 0? This is 1, so this is harmless and you just have this. So all we got to do is to look at the small s behavior of this guy here. If psi tilde of s equal to 1 plus order s analytic, then this gives you an s here, you get an s squared and the inverse Laplace transform of s squared is t. Diffusive behavior, you have normal diffusion. Everything therefore depends on the small s behavior of this or the large t behavior of the waiting time density. If it is exponential or anything which has got a Laplace transform which is analytic at s equal to 0, the first term is order s other than 1, then immediately you have diffusive behavior in general. But suppose it turns out that if psi tilde of s equal to 1 plus s to the beta, order s to the beta less than 1, not analytic like square root of s for example. What is going to happen is that this whole thing is going to go like 1 over s to the 1 plus beta, because this 1 cancels and you have s to the 1 plus beta. And what will it imply for the mean square displacement? Which is subdiffusive. This is the famous anomalous diffusion. It is entirely therefore dependent on the long tail behavior of psi of t, because what does it mean if for instance psi of t went like 1 over t to the 3 halves? What would it mean for the Laplace transform? This guy. You have to take the Laplace transform of t to the alpha, where alpha is minus 3 halves. So that is 1 over minus 3 halves plus 1, which is s to the half on top. So this will immediately tell you that this fellow here would not be true, you would get s to the half. That will immediately lead to subdiffusive behavior, which says the mean square displacement will go like the square root of the time rather than the time itself. So the root mean square behavior will go like t to the 1/4 in that case. It is slower than normal, subdiffusive. And there is a huge literature on anomalous diffusion, the practical implications of anomalous diffusion, etc. We will say a little more about this. But this is one mechanism by which you can see a huge variety of behavior will emerge, and it is essentially exact. We have solved the problem on an arbitrary lattice, and we have seen that everything depends finally on this waiting time density. What its long tail behavior, if it has a long tail, then you have anomalous diffusion. Okay. If on the other hand it cuts off exponentially, then its Laplace transform is analytic at s equal to 0, and then you do not have any problem. You have normal diffusion. The process is still non-Markov as soon as you do not have an exponential waiting time density, but it could lead to all kinds of anomalous diffusion if this has a long term tail here. So we have done this without actually writing down a master equation for P of j comma t, which we can't in the normal in most non-Markovian cases. So we did this by this trick of writing down generating functions and then looking at the statistics of the time, the step distribution separately from that, the geometrical problem of finding out where you are on this lattice and so on. We can go ahead with this and find first passage time distributions, recurrence properties and so on and so forth. These are matters of detail, but I thought this will give you some idea of how anomalous diffusion arises, how this non-analytic behavior arises. Okay. Let me stop here today.